People assume that Earth has always been alone in the sky with just one moon. That's what we know, what we see when we look up on clear nights. But the truth is far more fragile than that. Our celestial arrangement is not inevitable at all. In the vast, improbable history of our solar system, Earth could have easily ended up with two moons rising together, casting their light across the same night sky. And if you've ever wondered what that world might look like, what it might feel like to live under two lunar companions instead of one, then you've come to the right place. We'll be exploring that possibility together over the next hour, moving slowly through the science and the wonder of what that transformation might mean. If you find yourself drawn to these kinds of slow, grounded explorations, the kind where we take a what-if seriously and follow it into all its implications, both beautiful and strange, consider subscribing for more journeys through impossible skies and imagined worlds like this one, all designed to unfold as you drift towards sleep. Now, imagine it's twilight. The sun has just slipped below the horizon, and that first moment of dusk has arrived, that suspended, in-between time when the sky holds neither day nor full night, but something quieter, something in the hush between the two. Imagine you're standing on a shore, any shore, and the ocean stretches out before you like a mirror, catching the last ember of daylight. The water is still, almost impossibly still. The waves are gentle, whispered things against the sand, and there's no sound except the soft, rhythmic breath of the tide. And then you notice something has changed. Something about the light, the quality of the air. You look up. There, just above the horizon where the first stars are beginning to prick through the softening blue, something is rising, a pale luminescence, creeping upward from the edge of the world. It's the moon. But as you watch, as your eye follows that gentle arc of light, you see something else beginning to rise just beside it. Another pale form, slightly smaller perhaps, or of a different shade, one warm and honeyed, the other cool and silver grey. Two moons, rising together, rising as if they've done this every night for billions of years, rising as if it's the most natural thing in the world. The first moon clears the horizon fully, and its light begins to spill across the ocean in a long, luminous path toward where you stand. Then the second follows, and another path of light spreads across the water, intersecting the first, doubling the brightness, changing the angle of every shadow on the beach. The light is brighter than you've ever seen it on a moonlit night, yet softer somehow, more complex. Where the two illuminations meet, strange geometries form. Where they diverge, there are pockets of shadow that feel deeper than they should. The whole world beneath the twin moons is redrawn. Colors that shouldn't be visible at night become faintly distinguishable. The sand is no longer a simple grey or gold, but holds subtle variations. The water is not one shade of dark silver, but shifts and moves with the interplay of light from two different sources. If you've ever stood beneath a full moon alone, you know that strange clarity it brings. Not the clarity of day, but something else entirely, a nocturnal clarity. A way of seeing that belongs to night rather than to day, that activates something ancient in the human mind. Now imagine that sensation doubled. Imagine a night bright enough that shadows matter. Imagine trying to navigate by two lunar bodies that don't always align, that create a more complex grammar of light and dark. Behind you, inland, sounds are beginning to stir. Night birds perhaps, or insects, awakening to the change in light. The ocean continues its gentle work against the shore, but even that rhythm feels different somehow, slower, more ceremonial, as if the tides themselves, knowing they would soon be ruled by two moons instead of one, are still learning how to move. The sight would have been impossible, of course, in Earth's actual history. Two moons rising like this would require a chain of cosmic coincidences so precise, so delicately balanced, that the wonder isn't that we ended up with two moons, it's that any world ends up with any moon at all. And yet the universe has achieved stranger things. The universe, in fact, is built on precision like this. And so we're going to walk through how this impossible night might have come to be, following the threads of physics and probability backward through time, asking at each step, why couldn't this have happened? What stands in the way? What would have to shift, just slightly, for the sky above us to split its loyalty between two celestial bodies instead of one? But for now, stay with that image. Stay with those two moons rising. Let that light spread across the water. Let your eyes adjust to this new configuration of night. Let the familiar made strange settle around you. The beach, the ocean, the sky, all rendered different by the addition of one more silver body. This is the world we're going to inhabit, at least for a little while. This is the night sky we're going to learn to read. And there is something deeply peaceful about standing under such light. Something that speaks to a part of us that has always wondered what the world might look like if history had taken one different turn. If gravity, billions of years ago, had arranged things just slightly otherwise. If there had been one more wanderer in the sky, one more light, one more companion for the long night. If you find yourself drawn to questions like these, to the strange geometry of worlds that don't exist but could have, to the patient unraveling of how small changes in cosmic chance ripple across entire histories of light and life, then there's something waiting for you in the corner of this channel, where we gather to explore slow, immersive journeys through impossible skies and the imagined worlds that hang just beyond the edge of what is. We believe that the best way to understand our own reality is sometimes to walk, in thought, through the threshold of another one. Not as fantasy, but as a kind of deep listening to the physics and chemistry and biology that underlie all possible worlds. Each story we trace here begins with a real question, a genuine what if, rooted in actual science, and then we follow the thread, gently, without rushing, to see where it leads, where the tides would go, how the nights would change, what the ancient peoples might have called these twin silver siblings hanging above them. Please consider subscribing if this kind of slow, science-grounded dreaming calls to you. It's the easiest way to return to these threshold worlds whenever you need them, to drift again through the thought experiments and the speculations and the real discoveries that hide inside them. No advertisements, no sudden transitions, just the kind of long, patient unspooling of ideas that asks you to think and rest at the same time. For now, though, let's return to our twin moons, still rising together over that imagined ocean. Because to understand how Earth could have ended up with two satellites, we need to travel back through billions of years, to a time when the solar system itself was still learning how to hold its shape. Our own moon came to be through an event so violent, so improbably perfect in its timing and geometry, that it took planetary scientists decades to piece together the truth. There was a time, you see, when the young Earth was not alone in quite the way we imagine it now. 4.5 billion years ago, in those first fevered centuries after our planet had coalesced from the solar nebula, the inner solar system was a crowded, restless place. Countless bodies of stone and ice tumbled through space in trajectories that would seem chaotic to our eyes, yet were governed by gravity's patient mathematics. And among these wanderers was something truly massive, a protoplanet roughly the size of Mars, now called Theia, though no one was there to name it then. What scientists believe happened next, and this is the giant impact hypothesis, the prevailing theory for the moon's origin, was a collision of such precise proportions that it seems almost miraculous in retrospect. Theia, moving at an angle across the early solar system, struck the nascent Earth not head-on, but at a shallow, glancing blow. The angle and speed of impact were crucial. Had Theia hit us straight on, it would likely have shattered both worlds into rubble, scattering the fragments outward, where they would have recombined into something utterly different, if they recombined at all. Had it struck at a different velocity, the consequences would have been equally dire or equally strange. But this particular collision, at this particular moment, with this particular trajectory, tore away a vast disk of molten material from both the impactor and from Earth's outer mantle and crust. This debris, still hot and still gravitationally bound to the Earth, began to orbit our planet at a distance measured in thousands of kilometers, and within a span of months, or perhaps a few years, a blink of an eye in cosmic time, these fragments gathered themselves, pulled by gravity, into a single body. Our moon was born from catastrophe. Now consider how many variables had to align for this to happen. Consider the near misses, the close calls in Earth's early history that might have produced not one moon, but 2 or 3 or a dozen. The solar system was full of such bodies, planetesimals and protoplanets and wandering mountains of stone, each one a potential moon if only the geometry had been slightly different. If Theia had struck at a steeper angle, it might have deposited additional material that formed a separate satellite in orbit. If a second large impactor had arrived a few million years later, Earth might have accumulated another moon from that collision's debris. The reason Earth settled on a single, relatively large moon was not inevitability. It was chance, pure and refined through the crucible of celestial mechanics. This is worth sitting with for a moment. The moon we see rising every night, that pale companion that has watched over human civilization since before we had language to describe it, exists because of one particular event among countless possible variations. Our solar system as a whole has produced other double moon systems. Indeed, they exist in our neighborhood even now. The planet Mars, smaller and farther from the Sun, captured 2 small asteroids and holds them as moons, Phobos and Deimos, dancing their own peculiar orbits around the red planet. On the distant edge of our solar system, the dwarf planet Pluto and its companion Charon are locked in a mutual orbital embrace, so evenly matched in size that they orbit around a point in empty space between them rather than one orbiting the other. These systems are not relics of a different physics, not products of different rules. They emerged from the same solar system, governed by the same gravity, born from the same ancient bombardment and chaos that gave us the moon. The giant impact hypothesis itself is relatively young as scientific consensus goes. For much of the 20th century, astronomers debated the moon's origin fiercely. Some believed it had been captured from elsewhere in the solar system, a rogue body that had wandered into Earth's gravitational grasp like a stray animal finding shelter. Others proposed that the moon had somehow separated from the Earth itself, spun off by Earth's rotation in the distant past. These ideas were elegant in their simplicity, but they stumbled when tested against the evidence, against the moon's chemical composition, its orbit, its mass relative to Earth. The moon, it turned out, was too enriched in certain isotopes and too depleted in others for it to have been simply captured or simply spun away. It had to have formed from material that was partly Earth and partly something else. This was the genius of the giant impact hypothesis. It explained not only where the moon came from, but why it is what it is, why its properties match this singular, dramatic origin story. And here is where the thought experiment becomes particularly rich with possibility. If the early solar system had been even fractionally more densely packed with bodies, if the planetary migration patterns had been slightly different, if any one of hundreds of impactors had arrived sooner or later, traveling at a different angle or with a different velocity, then Earth might have acquired additional moons from multiple impacts. Imagine 2 or 3 impactor events, each one massive enough to tear away material, but not catastrophic enough to destroy the planet entirely. Each impact would contribute its own disk of debris, its own orbiting fragments that would coalesce into satellites. Or imagine a scenario where one of those protoplanets, instead of colliding with Earth, was captured into orbit around it. A rare event, but not impossible if the geometry aligned just right. The solar system is not a place of perfect efficiency. It is a place of collisions, near misses, and improbable outcomes. The fact that 2 moons did not form around Earth is not a law of physics. It is a historical accident. It is the record of specific events that happened to occur, written in the positions of planets and the compositions of moons. And this accident, this particularity of our world, is worth contemplating as we imagine what might have been. For if a second moon had formed alongside the first, it would have set in motion a cascade of consequences, some subtle, some profound, that would have rippled through Earth's entire history, through the shape of the continents, the rhythm of the tides, the course of life itself, and the dreams and religions of any humans who might have evolved to witness it. Picture, if you will, the solar system not as it is today, orderly, settled, almost mechanical in its predictability. But as it was 4.5 billion years ago, the young Earth did not orbit alone in a quiet void. Around it swirled a vast archipelago of fragments, asteroids the size of mountains, planetesimals ranging from the scale of cities to the scale of small worlds. Some of these bodies were themselves proto-moons, each one a candidate to become a permanent satellite, each one tumbling through space on trajectories that would determine whether they would be captured, collide, or drift away into the deeper darkness. The early solar system was, in essence, a crowded place. Where we now see vast stretches of emptiness between the planets, there once existed a thick haze of debris left over from the formation of the Sun itself. As gravity began to sort this primordial material into larger and larger bodies, Earth was surrounded by an entire swarm of would-be satellites, each one pulled by the planet's gravity, each one influenced by the gravity of its siblings and by the lingering tug of the young Sun. It was a realm of constant near misses and narrow escapes. Imagine a proto-moon the size of our Mercury, drawn by Earth's gravity into an orbit that brought it dangerously close, but then, perhaps, the gravity of another fragment just slightly altered its path, and it was flung outward instead, eventually to be captured by Venus, or to drift into the inner solar system. Another object, smaller but moving with tremendous speed, grazed the outer edges of Earth's gravitational sphere of influence, came close enough that for a moment it seemed it might settle into a stable orbit, but then the tidal forces from nearby bodies pulled it away, back into the chaotic dance. The solar system of that era was not governed by quiet, eternal laws. It was a place of violent and rapid change. Large bodies collided with smaller ones. Smaller bodies merged together, forming larger ones. Gravitational encounters scattered objects across enormous distances. Some bodies spiraled inward toward the Sun, their orbital energy dissipated through friction with the cosmic dust and gas that still permeated the system. Others were ejected entirely, flung out into the darkness beyond, perhaps to become rogue planets drifting alone through the galaxy, never to orbit any star again. And all of this time, Earth itself was accumulating material, not steadily, not gently, but in violent episodes punctuated by long periods of relative quiet. Each collision added mass, added heat, added angular momentum to the planet and its nascent system of satellites. Some of the impacts were so catastrophic that they briefly vaporized the outer layers of the planet. Others were gentle enough, relatively speaking, that small fragments could be incorporated into the planetary crust without fundamentally altering its character. The peculiar thing about the early solar system is how sensitive it was to small variations in initial conditions. The difference of a few degrees in the angle at which a proto-moon approached Earth, or a difference of a few percent in its velocity, could mean the difference between capture and escape. Some objects that came close to being captured were deflected by the gravity of other bodies nearby. Others that might have been flung away were instead drawn into stable orbits by fortuitous gravitational interactions. It was, in many ways, a lottery, and the solar system we inherited is simply one of an almost infinite number of possible outcomes. Yet within this chaos, there were islands of relative order. Certain orbital configurations were more stable than others. A body placed at a distance of roughly 3 times the Moon's current orbital distance, for instance, would have faced constant perturbations from the other debris surrounding Earth, but it might have persisted for a time before being either ejected or drawn closer. The mathematics of gravitational interaction, which seem so deterministic when we observe the solar system today, appear almost random when applied to these crowded early conditions. Consider the possibility of a second body, comparable in mass to the Moon, but still slightly smaller, arriving at Earth during this tumultuous period. It might have been drawn from the inner solar system, where most of the solar system's rocky material was concentrated, and it might have been nudged by the gravitational influence of other bodies, or by drag from the cosmic dust and gas, into an orbit around Earth. If its arrival coincided with a period when the existing population of Earth-orbiting bodies was slightly depleted, if, that is, several proto-moons had recently been ejected or had crashed into Earth itself, then this new body would find itself in a relatively peaceful neighborhood, at least for a time. The presence of two large bodies orbiting the same planet would have created a gravitational landscape of extraordinary complexity. The two proto-moons would have exerted forces on each other, gradually altering their orbits. At some points in their dance, they might have approached each other closely enough that tidal forces would have been significant, heating their interiors and potentially triggering volcanic activity on their surfaces. At other points, they might have retreated into nearly independent orbits, responding primarily to Earth's gravity rather than to each other. Whether two moons would have remained stable under these conditions depends on details that we can only speculate about. The mass ratio between them, the precise geometry of their orbits, the intensity of the gravitational perturbations from other debris still surrounding the young Earth. All of these factors would have played a role. Some configurations would have been stable enough to persist for millions of years, perhaps eventually settling into the long-term stability we observe in the solar system today. Others would have been unstable, leading inevitably to a collision between the two moons, or to the capture of one by another body, or to the ejection of one of them from Earth's gravitational system altogether. What we know with certainty is that chaos and chance governed the early solar system. What we can observe is the legacy of that chaos in the solar system as it exists today. The particular distribution of planets, the particular masses of the Earth and Moon, the particular tilt of Earth's axis, the particular configuration of asteroids in the asteroid belt, all of these are remnants of the violent and chaotic processes that played out in the first few 100 million years after the Sun's formation. Earth easily could have captured not one moon, but two, or three, or many. That it captured only one is, in a sense, the product of an elaborate cosmic coincidence. Now imagine this moment of dual moonrise, not as a distant fantasy, but as something that could have genuinely happened in Earth's deep past, something written into the mathematics of orbital mechanics. To hold a second moon in stable orbit requires a delicate balance of conditions, invisible forces arranged just so, like a mobile suspended in still air, where every mass and distance matters profoundly. The first constraint is mass. Our second moon cannot be just any wandering object. For it to remain captured in Earth's gravity well, and not spiral away into the void, it would need to be substantial enough that Earth's pull could hold it reliably through the millennia. Yet it cannot be too massive, or it would dominate Earth's own motion, making our planet the satellite and the moon the primary body. There exists, in other words, a Goldilocks range. Consider that our actual moon is roughly 1/27th of Earth's mass, a relationship that emerged from that singular giant impact 4.5 billion years ago. A second moon settling into this system would likely need to be somewhat smaller, perhaps a quarter or a fifth of our moon's size, giving it perhaps the mass of a large asteroid or a modest planetesimal. This is not incomprehensibly large, but substantial enough to hold its shape against its own gravity, to maintain an orbit without constant external coaxing. Distance from Earth becomes the second critical variable, and here the constraints tighten considerably. Too close, and tidal forces would tear the moon apart, rending it to fragments and dust. Each piece would then slowly fall toward Earth, creating a system of rings perhaps, or a slow rain of meteorites spanning millennia. We know this happens in our own solar system, where Saturn's Roche limit defines the distance below which a moon cannot survive intact. For our hypothetical second moon, maintaining enough distance to resist this gravitational shredding would mean placing it somewhere in the region beyond Earth's synchronous orbit, the altitude at which a satellite's orbital period matches Earth's rotation. This typically sits around 36,000 kilometers up for Earth-sized planets, though the exact figure depends on the satellite's characteristics. Yet simply being far enough is not sufficient. The moon must settle into what astronomers call a stable orbit, a region where gravity and motion balance in a sustainable way. Think of it as a groove in space-time itself, a path where the moon naturally wants to stay, like a marble rolling perpetually along the bottom of a curved trough. This is not assured. In the solar system's early age, when dozens of proto-moons and planetary embryos crowded near Earth, stability was precious and rare. Many objects were ejected, Others collided, still others merged. Our second moon would have needed to find its groove, to discover that exact combination of distance and velocity that permits it to orbit without gradually spiraling inward or veering outward. The relationship between these moons themselves introduces another layer of complexity entirely. Two moons orbiting the same planet do not ignore each other. Their gravity reaches across space, each one tugging on the other, especially when they come closest in their respective orbits. This mutual gravitational interaction must remain gentle enough that neither moon's path becomes too distorted. If the orbits were too close, or if the moons were moving in certain resonant patterns, they could actually amplify each other's wobbles over time, potentially destabilizing both. This is why Jupiter's 4 large moons, for instance, exist in what are called mean motion resonances. Their orbital periods relate to each other in simple ratios, like 4 to 2 to 1, arrangements that actually enhance stability rather than threaten it. Our hypothetical second moon would similarly need to find a rhythmic harmony with Earth's existing moon, a mathematical relationship that keeps both partners in balance. The slow physics of this arrangement reveals something profound about the universe's preferences. Stable orbits are not rare, but neither are they infinitely plentiful. They are islands of predictability in a sea of chaos, zones where gravity's equations permit long-term equilibrium. Our second moon, in this scenario, would need to have arrived or formed in precisely such a zone, captured at the right moment with the right velocity and mass, or else born there from the collision or aggregation of smaller bodies. How likely would this have been? Not impossible, certainly, but specific enough to make us wonder whether our single moon is itself the product of great fortune, or whether in countless worlds orbiting countless stars, two moon systems are perhaps more common than we might assume from the perspective of our one lonely satellite hanging in our own dark sky. Now imagine standing on a cliff top on an evening in this alternate Earth, watching the sky deepen from amber into violet, and there, rising together above the darkening horizon, not one moon, but two. The larger of the pair, perhaps something close to the size of our own familiar moon, emerges first, its surface a pale silver grey, cratered and weathered by the same cosmic bombardment that shaped it across billions of years. Then, trailing slightly behind and to its side, the second moon rises, smaller, perhaps half the diameter of its companion, and coloured differently, carrying in its reflected light a faint peachy orange hue that speaks of different composition, different rocks, a different story of origin. Together they climb, two distinct celestial bodies in the same night sky, and for a moment there is no sound but the wind and the distant pulse of waves below. The sight would have been unmistakable to any observer on Earth's surface, ancient or modern. There would be no question, no moment of doubt. Two moons, undeniably present, undeniably real, moving at slightly different speeds, tracing separate paths across the constellations. And yet for thousands of years, humans living under such a sky would have made sense of it in the only way we know how, through story, through naming, through the weaving of myth around what they saw. What names might they have chosen? The question is delightful to consider, because our ancestors were not indifferent to the sky. They were observant, curious, capable of noticing subtle differences and building elaborate meanings around them. The larger moon, perhaps resembling our own in size and brightness, might have been given a name resonating with power, rulership, clarity, something primordial and steady. In many ancient cultures, the moon was already associated with the feminine divine, with cycles and timekeeping, and the tides that shaped human survival along coastlines. Perhaps the greater of these two moons would have assumed that role entirely, given names like Luna or Selene in the Mediterranean imagination, or Hecate in her triple aspect, now split across two celestial bodies instead of one. Or perhaps, and this is equally plausible, the larger moon would have been masculine, associated with night journeys, with hunting under starlight, with the passage of time measured in months and seasons. The smaller moon, glowing with that peachy, warmer tone, would have invited different mythological architecture. Smaller bodies in ancient astronomy were often understood as attendants, companions, servants to the greater lights. Yet there was also something intriguing in its difference. Its distinct color would have been obvious even to the naked eye, even without modern spectroscopy or reflection photometry to explain why the hues diverged. That difference would have demanded explanation, and ancient peoples were masterful at generating explanations through narrative. Perhaps the smaller moon was understood as a younger sibling, still learning, still finding its place in the nocturnal realm. Or perhaps it was a refugee, a wanderer captured long ago and now bound to Earth's gravity, condemned to dance with the greater moon in an eternal courtship. The color alone, that warm peachy glow, might have suggested connection to fire, to hearth, to something more intimate and domestic than the cool silver of the primary moon. In some cultures it might have been understood as sacred, even dangerous, a sign of warning or blessing, depending on which tradition was weaving the narrative. Consider how these two moons would have moved across the sky, each with its own period, its own rhythm. The larger moon, assuming it orbited at a distance and velocity not so different from our own moon, would have cycled through its phases over roughly 28 to 30 days, a rhythm that would have synchronized easily with human menstrual cycles and the earliest calendrical systems. The smaller moon, depending on its orbital placement, might have had a different period entirely, perhaps faster, circling more quickly, completing its cycle in 20 days or even 15. To observers who kept careful count, and many ancient cultures were remarkably careful astronomers, leaving records in stone and clay, this would have been obvious. Two distinct periodicities, two separate calendars, in a sense, both running simultaneously. The mathematics of it would have been complex, intriguing, ripe for symbolic meaning. Perhaps one moon was understood to govern the seasons, the other to govern the tides. Perhaps one watched over the land, the other over the sea. The conjunction events, moments when the two moons passed close to one another in the sky, or even overlapped from Earth's perspective, would have been occasions of cosmic significance. Such events would occur periodically, the two moons drawing near, and then separating again, as their orbital mechanics dictated. In cultures that understood the sky through religious or astrological frameworks, such meetings might have been interpreted as conversations between deities, as moments of special power or danger, as omens requiring careful interpretation by those trained to read the heavens. Ancient records of the night sky are filled with such interpretations, with careful notation of celestial events and their presumed earthly consequences. Two moons would have doubled, tripled, exponentially increased the celestial phenomena available for mythological elaboration. And then there were the eclipses, or rather, the new possibilities for eclipses. With a single moon, a solar eclipse is a discrete event, the moon slipping directly in front of the sun from Earth's vantage point, its shadow racing across the landscape. With two moons, the geometry became more complex, more varied, more visually dramatic. Depending on the orbital configuration, one moon might eclipse the sun, while the other hung visibly nearby in the sky, creating a strange duality, a light and a shadow occupying the same moment. A smaller moon might occult the larger moon, creating a lunar eclipse of unusual character, the shadow of one companion falling across the face of the other. Or, in certain configurations, both moons might pass in front of the sun in quick succession, creating darkness and darkness again in the space of an hour. The eclipse narratives, the stories built around these events, would have been different in tone, more complex in their meanings, richer in their possibilities for human interpretation. What would the tides have looked like, from the perspective of an ancient observer standing on a beach in this imagined world, watching the waters rise and fall in response to two gravitational sources rather than one? That answer lies in the physics that follows, but for now, it is enough to imagine the ancient human being struck by a simple observation. The waters were more restless, perhaps, more animated, responding to forces that were visibly complex. Two moons in the sky, two centers of gravitational pull, two sources of tidal forcing. An ancient astronomer, patient and careful, watching the waters for years or decades, would eventually have noticed that the tides did not follow a simple pattern. They were modulated, varied, influenced by whether the two moons were aligned, opposed, or at some angle to one another. The complexity itself would have been understood as meaningful, as evidence of a cosmos that was alive, that was thinking, that was communicating through the language of geometry and light. If you have ever stood at the edge of a beach as the tide withdrew, feeling the pull of an invisible hand drawing the ocean back from the shore, you have experienced the most direct gravitational conversation between two bodies that most humans ever witness. The moon pulls the Earth's waters toward it with the gentleness of gravity, the same force that holds us to the ground, yet subtle enough that it raises mountains of water across entire ocean basins. Now imagine that conversation happening not with one lunar voice, but two. The physics of tides rests on a simple principle wrapped in complexity. The moon does not actually pull the ocean uniformly. Instead, the side of Earth facing the moon experiences a stronger gravitational tug than Earth's center does, and Earth's center experiences a stronger tug than the far side. This creates a stretching, a bulge of water facing the moon, and counterintuitively, another bulge on the opposite hemisphere. The bulge facing the moon is pulled toward it directly. The bulge on the far side arises because Earth itself is pulled more strongly than the water there, leaving the water behind in a sense. As Earth rotates beneath these two bulges, most coasts experience 2 high tides and 2 low tides each day, a rhythm so ancient it has shaped every port, every harbor, and every tidal pool for billions of years. With a second moon in orbit, this elegant dance becomes a duet, performed by 2 musicians playing simultaneously. Imagine that second moon rising into a slightly different orbit than our familiar satellite, perhaps moving at a different speed, passing over different latitudes. Where they aligned in the sky, their tidal forces would reinforce one another. The bulges would grow taller. High tides would be extraordinarily high, and low tides would retreat farther than they do now, exposing vast stretches of seabed that today remain underwater. The tidal range, the difference between high and low tide, would increase dramatically in many locations. Some coasts might experience tidal swings of 40, 50, even 60 meters in extreme cases. Yet this reinforcement would be fleeting. As the 2 moons moved at their different orbital speeds, they would gradually drift out of alignment. When they were positioned opposite each other in Earth's sky, something more complex would occur. One moon would pull the waters toward itself, while the other pulled them away. The tides would become confused, smaller, perhaps nearly cancelling each other out in certain regions. A coastal town might experience the strange phenomenon of slack tide lasting for hours, the ocean barely moving, neither advancing nor retreating. Then gradually, as the moons shifted position once more, the dominance would return to one satellite or the other. The tidal patterns would have become far less predictable, far more varied from day to day and month to month. This rhythmic unpredictability would ripple through the life that depends on tides. Tidal zones are among Earth's most intensely inhabited ecosystems. Barnacles, mussels, starfish, and anemones cling to rocks in the intertidal zone, adapted through millions of years to rhythms so regular they could be read like a clock. They have developed behaviors keyed to the precise timing of high and low tide. Certain species spawn only when tides reach specific heights on specific lunar phases. Some fish migrate into tidal flats to feed during low tide, returning to deeper water as the water rises. The regularity of our current tides, with their predictable 2-per-day cycle and their monthly variations tied to lunar phases, has been written into the bodies and behaviors of marine organisms as surely as circadian rhythms are written into creatures of the day. A dual moon system would force a wholesale renegotiation of these ancient agreements. Some tidal zones might experience tidal ranges so extreme that they become habitable by only the most resilient organisms. Creatures that could barely tolerate desiccation in our current world might become irrelevant, stranded too far above the new high tide mark. Others, in regions where tidal forces partially cancelled each other, might find themselves suddenly less exposed, able to inhabit shallower intertidal regions than before. The entire architecture of the tide pool would shift. The gradient from fully aquatic to fully terrestrial would become steeper or gentler, depending on the local configuration of the two moons. The mangrove forests, those cryptic tangles of roots that shelter fish and birds in the subtropics and tropics, depend on a particular range of salinity and water level maintained by predictable tidal cycles. Seagrass meadows, which carpet shallow coastal waters and support vast numbers of creatures, have grown their distribution patterns around tidal expectations. Salt marshes, those liminal zones where land and sea embrace, have evolved their plant communities, their sediment profiles, their layering of mud and salt around the rhythm that tides provide. All of these would reorganize themselves around new tidal regimes, a process that would unfold over centuries or millennia, but no less profoundly for the slowness of it. The energy equation would shift as well. Tidal energy is real energy, heat dissipated in the friction between moving water and the Earth's surface. In some regions on our current Earth, the tidal energy is so immense that it has been channeled into artificial infrastructure, tidal barrages that extract electricity from the flowing and ebbing tides. A world with two moons and stronger or more variable tidal forces would be a world where more energy was being continuously dissipated in tidal friction. How much more? That depends on the configuration of the second moon, its mass, its orbital distance, all the particular parameters of this imagined scenario. But the effect would be real, measurable, a subtle heating of the planet's oceans and a tiny acceleration of the tidal locking process by which moons gradually synchronize the rotation of their parent worlds. The daily and monthly cycles by which life itself is organized would become far more complex. Our current biology runs on nested rhythms, the 24-hour circadian cycle imposed by Earth's spin and the sun's movement, the 28-day lunar cycle that affects tides and has been observed to influence everything from human reproduction to the behavior of nocturnal animals. A second moon would introduce yet another cycle, a new period of orbital alignment and misalignment. Imagine that this secondary lunar period was, say, 33 days. Biological organisms would now be sensitive not just to the combined 28-day and 33-day rhythms, but to their interaction, creating a complex pattern that repeated only every 924 days, more than 2.5 years. Some creatures might evolve to track this longer cycle. Others might become confused by it, unable to predict when ideal tidal conditions would arrive. The evolutionary pressure would be intense. Coastal ecosystems have always been engines of evolutionary innovation. The tidal zone is where new strategies must constantly be invented because the environment is so demanding. A second moon would make it even more demanding, even more variable, even more unpredictable in the short term, even as the long-term patterns would eventually become decipherable. It would create new niches, new opportunities for organisms capable of tolerating extreme tidal ranges or thriving in the periods when tidal forces partially cancelled. It would also close off old niches, making certain strategies suddenly maladaptive. The result would be a reorganized web of life along every coast, different in details from the world we know, yet recognizable in its basic logic. The eternal negotiation between water and land, between the cosmic bodies overhead and the small creatures clinging to existence in the zone between them. Now imagine something far more subtle, though equally profound. These two moons, hanging in the sky above your imagined Earth, are not merely decorative, they are pulling, constantly, on the oceans and the stone beneath them. And as they pull, they are also slowly, invisibly, reaching into the very rotation of the planet itself. The moon we have today, our single moon, is already a sculptor of time. Over millions of years, it has been gradually slowing Earth's rotation. When the dinosaurs walked, a day was not 24 hours. It was shorter, perhaps 23 hours, or even closer to 22. The fossil record and the study of ancient sediments tell us this story, written in layers of rock and in the growth rings of creatures now extinct. Our moon, through its gravitational embrace and the friction it generates in Earth's oceans, has been a brake upon the world's spinning. It has been lengthening our days, one second after another, across the unimaginable span of geological time. But what if there were two such breaks? A second moon, positioned in its stable orbit, perhaps at a different distance, perhaps moving in a different rhythm through the sky, would exert its own gravitational pull on those same oceans. The tidal force would not simply double. The mathematics of gravity are more intricate than simple addition. Two moons at different distances, at different positions relative to Earth's equator, would create a far more complex pattern of tidal bulges. At times, they might work together, their pulls aligned, creating tides of extraordinary amplitude. At other moments, they might pull against each other, creating cancellations and interference patterns in the water itself. This is not mere decoration for the night sky. This is physics that would reshape the very rhythm of the world. The friction generated by these amplified tides, water sloshing across continental shelves, energy dissipated in the depths of the ocean basins, would accelerate the slowing of Earth's rotation. A day would grow longer, more rapidly, than it does in our own timeline, where our planet has taken billions of years to extend the day by a handful of hours. A dual-moon world might accomplish similar lengthening in a much compressed span of time. The rate of this slowdown is not a fixed thing. It depends on the exact configuration of the moons, their masses, their distances, their orbital characteristics. But the direction is certain. More tidal friction means faster deceleration of spin. Think of what this would mean across deep time. In our world, the day lengthens so gradually that no single human lifetime perceives the change. But if you could compress geological time, speed it up like a film, you would see the rhythm of the Earth shift before you. Sunrise would creep later, sunset would arrive earlier. The cycle of night and day would stretch like taffy pulled between two hands. And the creatures living on that world would need to adapt, or migrate, or vanish, as the very fundamentals of their circadian rhythms, the internal clocks that govern sleep, reproduction, feeding, and 1,000 other vital processes, no longer quite match the actual period of light and darkness. There is something else that matters too, something deeper still, the stability of Earth's axial tilt. Our planet spins on an axis that is tilted roughly 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is the reason we have seasons. It is also, in a sense, an accident of our deep past, the product of ancient collisions and gravitational influences that are now long settled. Yet the tilt is not perfectly stable. It wobbles, precesses, like a spinning top, gradually changing its angle. Over cycles of about 26,000 years, the direction of our axis traces a slow circle through space. This precession is caused, in part, by the gravitational influence of the Sun and Moon pulling on Earth's equatorial bulge. Now introduce a second moon, with its own gravitational pull, its own moment of inertia, its own interaction with Earth's shape and spin. The mathematics of orbital mechanics become substantially more intricate. The second moon might amplify the precession. It might dampen it. It might alter the frequency at which the precession occurs, or it might introduce new, secondary wobbles into the axis itself. The consequences could be profound. In our world, the slow precession of Earth's axis means that the pole star, that fixed point toward which our north axis points, gradually shifts. The bright star we call Polaris is our current North Star, but only by accident of timing. In the distant past, other stars held that position. In the distant future, others will. This slow shift does not catastrophically disrupt life, because it occurs across tens of thousands of years. But what if precession were faster? What if the axis wobbled more violently? The amount of seasonal variation, the distribution of sunlight and cold across the globe, the stability of climate zones, could all shift more dramatically. And here we touch upon something harder to predict, something more speculative, but still grounded in the physics we understand. There is a threshold, not precisely mapped, because the Earth system is extraordinarily complex, beyond which changes in axial stability might tip the climate into different modes. Not catastrophically, perhaps, but fundamentally. The distribution of ice and snow at the poles, the patterns of ocean currents, the reflection of sunlight back into space, all of these are sensitive to the angle at which sunlight strikes the planet. A more unstable axis might mean climate regimes that shift faster, that oscillate with different frequencies, that are harder for life to predict and accommodate. The single moon we possess has been, in some sense, a stabilizing force for Earth's climate and life itself. It has maintained our axial tilt within a narrow range. It has shaped our tides, and by extension, our oceans. It has slowed our rotation to a pace that allows complex life to evolve and flourish under rhythms that are neither frantically fast nor glacially slow. But it is a stabilization that is not inevitable. It is contingent. It is an accident of our particular history. A second moon might have made Earth wilder. The days would still turn, the seasons would still cycle, but the rhythm would be different, less settled, less predictable in the long run. Or it might not. The calculations are sensitive to the details, and the details, the exact masses, orbital periods, initial positions of these imagined companions, are beyond our knowing. What we can say, with confidence, is that the presence of a second moon would alter this fundamental clock. It would write a different story into the geology of the world. And yet, as the hours pass and both moons climb their separate paths across the night sky, something quieter and more intimate begins to transform. The light itself changes. Where once the Earth's night held a singular lunar glow, a familiar brightness that our eyes and hearts have learned over millions of years, now two separate sources cast their illumination downward, and the entire character of darkness shifts in ways both subtle and profound. Imagine standing in a landscape where two moons hang at different heights, perhaps one larger and warmer in tone, the other smaller, paler, casting a different quality of light altogether. The shadows beneath your feet would no longer fall in a single direction. They would layer and intersect. A tree might cast not one shadow but two, sometimes merging where the light sources align, sometimes diverging when the moons are at angles to one another. These double shadows would move across the ground as the two moons traced their separate rhythms, creating patterns that would shift throughout the night in ways that single moonlight never could. The brightness itself would be dramatically transformed. On a night when both moons were full and high in the sky, the illumination could be nearly as vivid as twilight. Colors that vanish in our current moonlit nights might remain faintly visible. The landscape would have a strange clarity, a kind of perpetual dusk that never quite surrenders to true darkness. On other nights, when the moons were at different phases or positioned far apart on opposite sides of the Earth, the night might feel more familiar, sometimes even darker than what we know, if one moon waned while the other had not yet risen. This transformed quality of light would ripple outward through the entire nocturnal world, affecting the creatures that have evolved for countless generations to navigate and hunt and hide within darkness. Nocturnal animals, after all, have built their entire sensory apparatus around the particular light conditions that our single moon creates. The tapetum lucidum, that reflective layer at the back of a cat's or owl's eye that glows in darkness and allows them to see with such remarkable clarity in low light, would need to function in a fundamentally different lighting environment. Whether this would be advantageous or challenging depends entirely on which creatures we imagine and how they might have adapted. Consider the hunting patterns of a nocturnal predator, perhaps a creature that has evolved something like a nocturnal hawk or an enhanced feline. For millions of years, this creature's eyes have been calibrated to the consistent, gentle glow that rises roughly once per month at full moon, a predictable rhythm of brightness and darkness. With two moons on different orbital schedules, the light levels available for hunting would fluctuate in far more complex patterns. Some nights might offer a hunter unparalleled brightness, an almost confusing abundance of light that renders camouflage far less effective. Other nights might present near total darkness, when both moons were below the horizon or in thin crescent phases simultaneously. The evolution of night vision itself might have proceeded along an entirely different trajectory. Perhaps these creatures would have developed even more sensitive eyes, capable of extracting every photon from whatever light was available, never quite knowing whether abundance or scarcity would greet them when they emerged at dusk. Or perhaps, conversely, the more complex and variable light environment would have selected for more flexible sensory systems, eyes capable of adjusting rapidly between the bright and the dim. The pupils of animals might expand and contract more dramatically. The retinas might maintain an even more sensitive balance between sensitivity and the need to avoid being overwhelmed by rare moments of intense illumination. And what of the creatures that rely on darkness itself as a refuge? There are nocturnal animals that have evolved not primarily to see well, but rather to move through darkness while being nearly invisible to their predators. A creature like a smaller rodent or a nocturnal insect might have evolved to be most active during the darkest parts of the night, when the moon is absent or new. In a world with two moons, these creatures' timing would need to shift. Their activity patterns, their circadian rhythms, might have synchronized not to a single monthly lunar cycle, but to the overlapping cycles of two separate moons, each with its own orbital period. The result might be a far more complex biological calendar, a layered set of activity peaks and valleys that occurred at different combinations of lunar phases. The bioluminescent creatures, too, would face a transformed world. Fireflies, certain fungi, deep-sea organisms that create their own light for communication or predation, all of these depend on their bioluminescence standing out against the ambient darkness. In a landscape sometimes brightened by two moons, the contrast between their self-generated light and the background would shift dramatically. Perhaps these creatures would have evolved brighter lures, more intense displays, in order to remain visible and communicative against a sometimes brightly lit sky. Or perhaps they would have developed the ability to modulate their brightness based on the current moonlight conditions, a kind of adaptive flashing that matched the external illumination. There is something poignant in imagining this, in recognizing how profoundly our night sky shapes the creatures that live beneath it. The rhythm of moonlight is not merely a backdrop for nocturnal life. It is woven into the very fabric of evolution, into the structure of eyes and neurons and internal clocks. A second moon would not simply double the light. It would create something genuinely new, a lighting regime that no earthly creature has ever experienced, and life would have to find ways to flourish within it. Think of the navigation cues that depend on moonlight. Many animals, from insects to birds to sea turtles, use the moon as a reference point for direction, a subtle compass that helps them find their way across vast distances. The position of the moon at a particular time of night, its height and angle, carries information embedded in their instincts, passed down through generations. With two moons on different paths, navigation would become exponentially more complicated. An animal would need to integrate information from two separate celestial sources, each on its own orbital schedule, each potentially offering contradictory directional information at different times of year. Some species might have evolved a kind of averaging system, somehow combining the positions of both moons into a coherent navigation signal. Others might have shifted their reliance to other stars, to the sun's residual glow at the edge of the horizon, to magnetism, to any of the backup systems that nature provides. The moon is also, we must remember, a timekeeper. The lunar cycle has synchronized human culture for millennia, governing our calendars and our ceremonies, but it has also shaped the internal clocks of countless creatures. Many marine organisms, from corals to crustaceans, time their reproduction to specific phases of the moon, a synchronization so precise that it seems almost magical when you first learn of it. In a world with two moons, this timing would shatter and reform into something new. Perhaps reproduction would be tied to rare moments when both moons aligned in particular phase relationships, making breeding seasons far more infrequent, or, conversely, far more frequent if the moon's cycles intersected at shorter intervals. The tides, which we have already discussed, would pulse to this same dual rhythm, and the creatures that depend on tidal cycles for their life history would need to evolve or adapt in concert with this new pattern. The quality of the moonlight that falls on a forest floor or a desert landscape would also change the way that plants responded to night. While most plant growth occurs in daylight, many plants retain light-sensitive mechanisms that adjust their physiology based on day length and nocturnal light levels. The increased brightness of a night lit by two moons might trick plants into slightly different growth patterns, might alter the chemical processes that occur during the dark hours, the cellular repairs and nutrient transport that plants conduct while the sun is down. It is subtle, perhaps, but present nonetheless. Another layer of the ecological transformation that would ripple outward from the simple fact of a second moon. The shadows on a moonlit night, too, carry a kind of meaning that goes beyond mere light and dark. Shadows provide information. A predator casting a silhouette becomes visible to prey. A prey animal leaving a shadow trace becomes vulnerable to hunting. The layered shadows created by two moons would complicate this ancient conversation between predator and hunted, between visibility and concealment. A creature might find itself visible to a predator under one moon's light, but hidden under the others, depending on the precise angle and phase of each lunar source. The advantage would shift moment by moment, night by night, creating a far more dynamic and unpredictable environment than the single moon world we know. And in those moments when both moons are high and full, when the night sky holds twice the illumination of our current fullest moonlit nights, there is something almost unsettling to imagine. The landscape would take on a clarity that feels almost unnatural to us. Creatures evolved under a single moon. The stars themselves might fade slightly from visibility, overwhelmed by the increased atmospheric scatter of light. The Milky Way, that ghostly river of light that defines the center of the night sky in dark places, might become fainter, its subtle beauty sometimes obscured by the brightness cast from below. This would be a loss of sorts, a trade of one form of beauty for another, a reminder that in reshaping the world's lighting, we would be reshaping not only the practicalities of vision, but the very aesthetic of the night sky itself. And yet, having imagined these two moons rising together, having watched them paint the sky in copper and cream, having felt their pull reshape the very tides beneath us, we must now turn our attention to something more intimate still, the delicate gravitational conversation that would unfold between them, night after night, century after century, in the infinite silence of space. For a second moon is never truly alone in its orbit. It would not simply hang there, obedient and still. It would dance with the first, in a partnership so finely balanced that even small changes in speed or distance could mean the difference between stability and catastrophe. Consider the gravitational forces at play. Our present moon orbits at roughly 384,000 kilometers from Earth, yet it also pulls upon itself through space. Now imagine a second moon, perhaps smaller, perhaps not, sharing that vast emptiness around us. These two would tug at each other constantly, each one's gravity reaching across the dark toward the other. The larger moon might find its orbit slowly adjusting, its path through space no longer a perfect circle, but something subtly elliptical, stretched and compressed by the presence of its companion. The smaller moon would feel these forces more acutely, more vulnerable to being pulled this way and that. The question becomes not whether they interact, but whether their interactions would eventually drive them toward each other, or whether some stable configuration could persist. This is where the concept of orbital resonance enters our story, gentle and profound. Imagine two pendulums hanging in the same room, swinging at nearly the same rate. If one swings a little faster than the other, something remarkable can happen. Their motions gradually synchronize. They find a rhythm together, a ratio of their orbital periods that becomes locked, like two dancers who have performed together so long that their steps anticipate each other without thinking. The moon and Earth are already in a gentle resonance of sorts. The moon's rotation is synchronized with its orbit, which is why we always see the same face of it. A second moon could fall into similar patterns with the first, their periods locked in ratios like 2:1 or 3:2, creating what astronomers call mean motion resonance. In such a state, the two moons would return to the same relative positions again and again, like two passengers on a Ferris wheel who meet at the same point every few rotations. This resonance, paradoxically, could actually provide stability. If the timing is right, if the orbital periods fall into one of those harmonic ratios, the gravitational pushes and pulls would happen in the same sequence every cycle, never accumulating in a direction that would destabilize the system. The moons would remain locked in this cosmic waltz, never wandering too far from their appointed paths. But, and here is where the thought grows more fragile, this stability depends upon beginning in precisely the right circumstances. There is a narrow corridor of possibility through which this arrangement must pass. What if the two moons were not in resonance? What if their orbital periods did not fall into one of those safe ratios? Then their gravitational interactions would be more chaotic. Imagine instead two dancers who cannot quite find a rhythm together, their steps perpetually falling out of sync. The gravitational tugs would happen at random moments in the orbital cycles, sometimes adding together, sometimes cancelling out, but never in a predictable pattern. Over time, these unpredictable forces could accumulate. One moon might be pulled inward, while the other drifted outward. Their separation would change, sometimes dramatically. In the worst-case scenario, and this is a scenario we must acknowledge as possible, the orbits could become unstable. One moon might be ejected from Earth's orbit entirely, cast out into the solar system as a rogue body, lonely and diminished. Or, in the opposite extreme, the inner moon might spiral closer and closer, until the tidal forces became so fierce that it would shatter apart, a victim of its own proximity. This is what happened, astronomers believe, in the ancient past around Jupiter. Its moons have been caught, released, crashed, and reformed countless times through the eons. The question that haunts this scenario is deceptively simple. How likely is it that two moons would find themselves in the kind of orbital resonance that allows long-term stability? The universe is vast and indifferent, and some configurations last, others do not. We observe this in our own solar system with the outer planets, whose orbits seem to encode ancient resonances, remnants of a chaotic early history. Yet we also see plenty of systems where bodies orbit without such neat numerical ratios, remaining stable through sheer separation and the dampening of gravitational effects over distance. A second Earth-Moon, if it existed, would need to be far enough from the first, and from Earth, that their mutual gravity did not overwhelm the system's coherence. It would need to orbit in a zone where three-body physics remained orderly rather than chaotic. These constraints narrow the possibilities, but do not eliminate them. Stability becomes not a certainty, but an achievement, requiring careful initial conditions and a degree of fortune. Picture the two moons at their moments of closest approach. They would not touch. Gravity would have arranged them carefully before any such collision, but the space between them might be measurable only in tens of thousands of kilometers. At such times, the gravitational strain would reach its peak. The nearer moon would be pulled slightly toward its companion, its orbit momentarily warped. The farther moon would feel the tug most acutely, its trajectory bent by the gravity of its distant sibling. These perturbations, these small disturbances, would ripple outward through the system. They would affect the tides on Earth, adding subtle variations to the already complex lunar dance. They would alter the tiny irregularities in day length, the minute wobbles in Earth's spin. Over geological timescales, millions of years, these could accumulate into significant changes. A stable double moon system, should one exist, would be one where these disturbances remained within certain bounds, never quite tipping the balance toward disaster. The two moons would maintain their careful distance, held apart by the same gravity that links them together, in a relationship that is simultaneously binding and repulsive, intimate and eternally separate. Now imagine this tranquility troubled. Imagine standing on that altered Earth, watching those two moons trace their silent paths across the night, and asking a question that has haunted mathematicians and astronomers for centuries. How stable could this really be? The answer, it turns out, lives in one of physics' most beautiful and unsettling territories. It lives in what scientists call the three-body problem. For centuries, the mathematics of the cosmos seemed elegantly simple. One body orbits another. Gravity pulls. Orbits are predictable, calculable, almost serene in their geometry. But add a third body to the dance, and something remarkable happens. The perfect geometry begins to fracture. The equations that once yielded clean solutions suddenly resist closure. The three-body problem, in its pure form, has no general algebraic solution. There is no final formula, no universal answer, only endless approximation and the creeping awareness that chaos lives very close to order. With two moons and an Earth, we have exactly this. Three bodies pulled by mutual gravity. Each exerts force on the others. Each force alters the trajectory of every other object in the system. In theory, the system could persist in stable equilibrium for an extraordinarily long time, perhaps even for billions of years. But in practice, the tiniest perturbations, a passing asteroid, the collective gravity of distant planets, the accumulated whispers of countless small bodies in the solar system, could nudge one of those moons into an unstable region of space where its orbit begins to unravel. The first moon, our original companion, might be particularly vulnerable to this destabilization. Our single moon is where it is now through what we might call a kind of gravitational compromise. It orbits at a distance where Earth's gravity holds it firmly, but not so close that tidal forces tear it apart. But the presence of a second moon would complicate this arrangement profoundly. That second moon would exert its own gravitational influence on the first. At certain points in their orbital dance, when the two moons align on the same side of Earth, they would pull together. At other moments, when they sat on opposite sides, the gravitational forces would create a kind of stretching effect. Our original moon would be yanked in competing directions. What would happen to the first moon under this sustained stress? The answer is that it would begin to drift. Not suddenly, not dramatically, but gradually, inexorably. Its orbit would grow wider, spiraling outward from Earth. Or, in other scenarios, it might spiral inward, drawn closer and closer to Earth's atmosphere, until, eventually, the tidal forces would overcome its structural integrity. The moon would break apart. Fragments would rain down. The catastrophe would be slow by human standards, but swift by geological ones. This is the fate that threatens many moons in the solar system, and it is written into the distant future of our own moon, though the timescale stretches beyond the lifetime of our sun. The moon is drifting away from Earth now, at a rate of about 3.5 centimeters every year. Eventually, in an unimaginably distant future, it will escape Earth's gravitational embrace entirely. But with a second moon present, this process might be far more violent. The perturbations would amplify. The dance would become a wrestling match, and the outcome would be written not in gentle equations, but in the language of collision and fragmentation. There exists another possibility, one that makes the mathematics even more intricate. The two moons might find what dynamicists call a resonance. Their orbital periods might settle into a simple mathematical ratio, 2 orbits of the smaller moon for every orbit of the larger, for instance. In this state of resonance, the gravitational tugs align in such a way that they reinforce each other rather than tearing at each other. The system locks into a kind of gravitational synchronicity, like two pendulums hanging from a beam, eventually swinging in a coordinated pattern. Two moons might find stability in resonance. But this resonance, if it occurred, would itself be fragile. The solar system is not an empty void. The gravity of the sun still dominates all motion at vast scales. The gravity of Jupiter, our cosmic neighbor, still whispers across the void. Occasional asteroids still pass through the inner system. Any of these perturbations could nudge one of the moons out of resonance, and once the synchronicity broke, the destabilization would begin anew. The deeper truth is that stability itself is an illusion in the three-body system. Mathematicians have discovered chaotic zones in such systems, regions of orbital space where predictability dissolves entirely. In these zones, two trajectories that begin impossibly close together will eventually diverge wildly. The future becomes unknowable. The mathematics surrenders. And in such a zone, our second moon might find itself trapped, its path through space a tangle of near misses and sudden accelerations. a random-seeming waltz between remaining bound to Earth and flying free into space. There is a particular species of instability that haunts planetary systems everywhere. It is called the Kozai mechanism, named after the astronomer who first described it in detail. In this dance, the orbital inclination of a smaller body begins to oscillate, while its eccentricity cycles in the opposite direction. An orbit that begins nearly circular might gradually become stretched and elongated. The moon that once moved in a comfortable path might suddenly be swinging in a wildly elliptical arc, careening close to Earth at one point and retreating to dangerous distance at another. If one of our two moons found itself caught in this mechanism, its fate would become a slow drama of orbital degradation and eventual disaster. Yet through all this talk of instability and chaos, there is a peculiar grace. The three-body problem, for all its mathematical intractability, often produces systems that can persist for remarkably long times. Many of the exoplanetary systems we have discovered in recent decades contain three or more massive bodies orbiting in configurations that should theoretically be unstable. And yet they persist, they dance, they find grooves and pathways through the space of possible orbits, strange attractors that hold them in quasi-stable configurations, even as the mathematics insists that true stability is impossible. A second moon might drift and destabilize. It might spiral inward or outward. It might eventually collide with the first moon or escape into space. But before any of these fates befell it, it might persist for millions of years. It might hold steady for an entire age of terrestrial life. And in those millions of years, life on Earth would evolve under its influence, would learn its rhythms, would weave its presence into the very fabric of adaptation and survival. The twin moons would become normal. They would become necessary. They would become home. And that is perhaps the deepest truth about the three-body system. Chaos and stability are not opposites. They are neighbors. They dance together. A system can be mathematically chaotic and yet practically stable. A trajectory can be unpredictable in detail and yet constrained within certain bounds. The universe does not demand that everything be simple or safe or eternally secure. It asks only that we accept the dance as it unfolds, finding wonder not in eternal certainty but in the delicate, temporary, precious balance that allows order to emerge from complexity, even for a little while. Now, as those twin moons would hang in your sky night after night, something far deeper and slower would be stirring beneath your feet. The ground itself would respond to this doubled celestial pull, and here we enter territory that is less certain, more speculative, yet grounded in the real physics of how Earth's interior works. Tidal forces, as we've explored, are not gentle suggestions from the heavens. They are actual stresses, real compressions and stretches of the planet's crust and mantle. Our single moon tugs at Earth's solid body as well as its oceans, though we feel and see those tidal waves far more easily. The solid Earth flexes, bends slightly, responds to this constant gravitational kneading. Imagine Earth as something between a rubber ball and a stone, rigid enough to hold its shape yet flexible enough to deform measurably under sustained pressure. Each day, our planet breathes in and out to the rhythm of lunar gravity. With two moons, that rhythm becomes infinitely more complex. The tidal stresses would not simply double. They would layer upon each other, sometimes reinforcing, sometimes conflicting, creating a far more intricate pattern of compression and extension that would ripple through the crust and down into the hot, moving rock of the mantle below. We must be careful here, because the precise effects would depend entirely on the moon's orbital positions, their relative masses, their distance from Earth. But we can ask, might this doubled tidal massage have consequences for the planet's most violent geological processes? Volcanic activity is fundamentally tied to the movement of Earth's interior. Hot rock rises, pressure builds beneath the crust, and when the stress becomes too great, the crust fractures and magma finds a path upward. The timing of volcanic eruptions, the frequency with which they occur, may be subtly influenced by the solid tidal stresses working through the crust. There is real evidence, gathered from observational data, that our moon does influence volcanic activity on Earth. The relationship is delicate and complicated, masked by many other variables. The deep convection of the mantle, the motion of tectonic plates, the slow accumulation of heat and pressure that operates on timescales of thousands and millions of years. Yet there does appear to be a small but measurable tendency for volcanic eruptions to cluster around times of extreme tidal stress, when the moon is at its closest point to Earth and pulling hardest. With two moons, those periods of extreme stress would become more frequent, more varied. Different regions of Earth might experience different patterns of tidal strain, depending on their position relative to the two orbits. Some areas might find themselves more frequently compressed, while others experienced extended pulls. Over very long timescales, this could theoretically alter the pattern and distribution of volcanic hotspots across the globe. The weak points in Earth's crust, the places where magma already wants to rise, might find new pathways upward, or existing pathways might be squeezed and redirected. And what of earthquakes? Here too, the connection is real but subtle. The stress in Earth's crust builds slowly along fault lines, plate boundaries, where two pieces of the lithosphere grind against each other. An earthquake occurs when that stored stress suddenly releases. The tidal stress from the moon, from gravity pulling on the solid Earth, adds one more tiny increment to the total stress accumulated along a fault. For most faults, most of the time, this tidal influence is drowned out by the far greater pressures of plate motion itself. Yet there is evidence that some earthquakes do show a slight preference for occurring during times of heightened tidal stress. The effect is small, but it is real. Now imagine that effect magnified, complicated, layered with the influence of a second moon. The patterns of stress would become more intricate. Faults that run north to south might respond differently to the gravitational pull of a moon approaching from the east than they would to one approaching from the south. Over geological time, this could theoretically alter the frequency and distribution of earthquakes, though we must whisper this carefully. We do not know if it would increase overall seismic activity or simply redistribute it. We do not know if the effects would average out to something close to our current reality or diverge dramatically. These are the limits of our certainty. What we can say with more confidence is this: tidal stress does propagate through the entire planet, from crust to mantle to core. Like the mantle itself, that vast ocean of hot rock that makes up most of Earth's volume, is constantly moving, churning in vast convection currents that drive plate tectonics. These convection currents are incredibly slow by our perception, moving inches per year, and they are driven primarily by the heat rising from Earth's interior and the weight of the plates above. Yet, the tidal flexing of the planet could add another influence, another tiny weight on the cosmic scales. The mantle convection patterns might shift slightly, subtly realigning the long-term currents of rock that underlie continental drift. Picture, if you can imagine it, a version of Earth where the grinding motion of the tectonic plates proceeds in patterns subtly different from ours. The Atlantic Ocean might spread at a marginally different rate. The Ring of Fire, that great circle of volcanoes rimming the Pacific, might pulse with slightly different intensity. The great collision zones, where continents crumple together and thrust mountains upward, might experience altered rhythms. Over millions of years, these small differences compound. The face of the planet shifts differently. Continents arrive at new positions on the globe, at times slightly different from our timeline. Yet we must hold this thought loosely. The tidal effects, while real, are small. The forces driving tectonic motion, the heat of Earth's interior, the weight of the plates, the resistance at subduction zones, these are vastly larger than the gravitational tugs from the sky. A second moon might nudge Earth's geology, but it would not overturn it. The planet would still have earthquakes, still have volcanoes, still have continents that move and collide. The basic character of Earth's geological personality would remain recognizably itself. What changes most profoundly is rhythm. Not whether the heart beats, but how often and in what pattern. A second moon would rewrite some of the subtle timing of Earth's geological pulse, the intervals between major eruptions, the clustering of seismic events, the rates at which plates move and mountains rise. And in a world where life has evolved to tune itself to the cycles of a single moon, those altered rhythms might have rippled through ecosystems in ways both large and small. Now we turn to perhaps the most intimate question of all. What would life itself become in such a world? The organisms dwelling in Earth's oceans, forests, and grasslands would not simply persist unchanged beneath this doubled lunar glow. Rather, they would be subtly reshaped, generation after generation, by rhythms that we might only recognize as estranged versions of their own familiar patterns. Consider first the most ancient calendar written not in stone or sky, but in the cells of living things. Many organisms on Earth today possess internal clocks that synchronize not merely to day and night, but to the lunar cycle itself, 29.5 days as it circles us now. Corals, for instance, time their mass spawning events to precise lunar phases, releasing eggs and sperm into the water on particular nights when the moon reaches a certain brightness and position. Certain insects, small crustaceans, and fish have all evolved to read the moon's monthly rhythm as reliably as you might read a calendar on a wall. But what becomes of such elegant synchronization when two moons of different sizes, different orbital periods, and different brightnesses trace their separate paths across the sky? The simple answer is that nothing would remain simple. A creature attuned to spawning when both moons were dark might find itself waiting for a window that never quite arrives, because one moon would be dark while its sibling hung nearly full. Over countless millennia, natural selection would have rewoven these biological clocks into something far more complex. Perhaps evolution would favor organisms sensitive to the combined brightness of both moons, creatures that could gauge the total illumination and respond accordingly. Or perhaps life would have fragmented into subpopulations, each synchronized to one moon or the other, or to particular combinations of their phases. The deep sea, that realm of profound darkness, might have evolved bioluminescent displays of staggering intricacy, as creatures learn to navigate by reflected light from two sources rather than one. The tides, as we touched upon before, would pulse across the oceans with a rhythm far more intricate than the one we know. This transformed tidal landscape would reshape the lives of the creatures that depend upon it. Along coastlines, the space between high and low tide, the intertidal zone, would become a realm of even more extreme challenge. Organisms living in tide pools would experience more violent fluctuations in salinity, temperature, and exposure to air. Some species might never have evolved to inhabit such margins at all. Others would possess adaptations we cannot quite imagine, perhaps thicker skins, more efficient water retention, or the ability to enter metabolic states of suspension more profound than anything we see in our world. Consider the great migrations that sweep across the planet every year. Countless birds time their journeys northward and southward, not only by day length but by subtle lunar cues, the angle of moonlight, its brightness at particular times of night. In a world of two moons, these navigational pathways would require relearning by every generation. Yet this is precisely how evolution works. The birds that happen to possess nervous systems flexible enough to integrate dual lunar information would find their routes refined and optimized. Over thousands of generations, migration routes might shift, expand, or contract. Certain pathways might become impossible, not because the landscape itself changed, but because the biological compass that guided travelers through the sky would need recalibration across epochs of time. The nocturnal animals, those creatures that have made night their domain, would inherit a fundamentally altered world. Moonlight, as it falls on Earth now, already provides a subtle illumination that allows many animals to forage, hunt, and move with greater precision than starlight alone would permit. But it also casts long, directional shadows that predator and prey alike have learned to read and interpret. With two moons, shadows would layer and multiply. A field mouse fleeing a hunting owl would find its escape routes illuminated or obscured, depending on which moon hung higher in the sky at any given moment. Over deep time, the eyes of nocturnal creatures might evolve different sensitivities, different distributions of rod and cone cells, adapted to pass a more complex visual environment. The pupils of a nocturnal cat or fox might narrow and dilate differently. Night vision itself, that realm of subtle greys and silhouettes that we barely understand even in our own world, might become a far richer sensory experience. But there is something deeper still. Many creatures possess what we call circadian rhythms, internal oscillators that tick to the beat of Earth's rotation, synchronized to the 24-hour day. Yet these rhythms do not exist in isolation. They communicate with seasonal rhythms driven by day length and temperature. They resonate with lunar cycles. In a world with two moons, the complexity of these nested, interacting rhythms would increase exponentially. A creature might need to track not 2 or 3 temporal cycles but 4, day and night, and the cycles of 2 different moons. This is not a fanciful scenario. There are real organisms on Earth whose behavior is governed by more than one periodic cycle, but the addition of a second moon would press this complexity to new extremes. Could an organism even evolve to track such intricate patterns? Neuroscience suggests that brains, in all their diversity, are fundamentally machines for pattern recognition and prediction. They evolved under selection pressure to anticipate the future based on past experience. A brain that could not learn to track a complex, multi-phased rhythm would be at a severe disadvantage. So yes, life would adapt. Perhaps in a dual-moon world, creatures would develop neural structures of startling sophistication, clocks within clocks, oscillators tuned to frequencies we have never observed in nature. Or perhaps, in an act of evolutionary pragmatism, life would simplify in certain ways, abandoning precise lunar timing altogether for more robust, flexible strategies of reproduction and migration. The deeper reflection is this: we often imagine that life as we know it is somehow fundamental, inevitable. That if you rewind time and replay Earth's history with slightly different initial conditions, you would arrive roughly at the same place. But evolution is not a march toward a predetermined destination. It is a continuous dance with the environment, a reshaping of possibilities. A second moon would not have merely changed the sky. It would have changed the very substrate of life's adaptation, the template upon which natural selection would compose its endless variations. The creatures that emerged would be as familiar and as alien to us as birds are to fish. They would share our chemistry, our DNA-based architecture, but they would be written in a different language altogether. And now imagine the human experience unfolding under these twin witnesses. Think for a moment about how deeply a single moon has shaped the way we measure time, navigate distance, and make meaning of the cosmos. A calendar built on lunar cycles, marked by the monthly dance of one moon alone, has governed the planting and harvest of civilizations. But what if, from the very beginning of human consciousness, there had been two? The earliest calendars might have emerged not from one lunar month, but from the interplay between two. Picture the first astronomers, the watchers of night sky, noticing that the larger of the two moons returned to the same position in the stars every 29.5 days, while the smaller one, orbiting closer and faster, completed its cycle in perhaps 17. The mathematics of this rhythm would have been written into every culture's sense of sacred time. They would have observed the moments when both moons rose together, aligning in rare and luminous conjunctions, and they would have named these events with reverence. Perhaps certain ceremonies only happened when the moons aligned. Perhaps the fastest moving moon, the one they could watch visibly change position from one night to the next, became the keeper of weeks, the marker of smaller time, while the larger moon held dominion over the greater wheel of the year. Consider how differently the Babylonians, those careful stargazers, might have developed their mathematics and astrology under a doubled moon. They would have tracked not one lunar node, but two, not one retrograde motion, but a complex dance. Their predictions would have required more sophisticated calculations, and in meeting that challenge, their mathematical systems might have evolved differently, perhaps more quickly, driven by the necessity of modeling this celestial duet. Would they have invented some form of calculus earlier, pushed forward by the gravity of prediction? The speculation is gentle, but it whispers through the history of human thought. Navigation across ancient seas would have carried a different geometry altogether. The single moon has always been a faithful compass of the night. A navigator knows that the stars wheel around the pole, constant and predictable, and the moon marks the passing hours through the darkness. But with two moons, each with its own speed and its own reliable path, ancient sailors might have developed a more intricate star map language. Imagine Polynesian wayfinders, those masters of watery distances, learning to read the angle between two lunar disks as precisely as they read the angle between stars. The second moon, depending on its size and color, perhaps a slightly reddish tone if it were smaller and older, or pale and close to silver if it were a captured asteroid, would have given them redundancy, a backup compass, and it would have given them complexity too. The night sky over the ocean would have been busier, richer, less forgiving of sloppiness. Perhaps their navigational traditions would have been even more elaborate, their teaching methods even more demanding, their mythology even more woven through with stellar knowledge. The religions that emerged would have inevitably mirrored this twin rhythm. Cultures shaped by single-moon cosmologies often saw the moon as feminine, as a measure of fertility and menstrual cycle and the tides of female power. But what does theology become when there are two? Would one moon have been seen as the eternal feminine and the other as a masculine principle? Would they have been lovers, eternally pursuing one another through the sky? Siblings, parents and child, creator and created. The dualism might have deeply shaped every theology that arose. The tension between unity and multiplicity, between the one and the two, would have been written into the earliest creation myths. The chase between the moons might have become a metaphor for the eternal struggle between opposites, light and shadow, growth and decay, becoming and unbecoming. Or perhaps they would have been seen as aspects of a single divine principle, and this might have inclined human religion toward a more unified, less dualistic cosmology than many that actually emerged. The arts would have transformed around them as well. Poetry in every tradition carries the fingerprints of the moon. Lovers have written to moonlight across every human culture, and the moon has been a symbol of constancy, of melancholy, of feminine mystery, of time's passage. But imagine the love songs written to two moons. The visual artists would have faced a different canvas altogether. The paintings of night would have had a different quality of shadow. Where a single moon creates a clear gradient of light and dark, two moons positioned even slightly differently would cast dual shadows from objects on the ground. A standing figure might have two shadows, one for each moon, a doubling of presence that would seem almost supernatural. In a world of two moons, this phenomenon would be commonplace, and therefore deeply embedded in artistic sensibility. Perhaps Renaissance painters, when they eventually came, would have treated the human figure as naturally double-shadowed. Perhaps the play of light and darkness would have taken on an almost nervous quality, a sense of being observed from multiple angles at once. Calendars themselves, those fundamental tools of synchronizing society, would have become more intricate and more contested. Should the agricultural year be based on the larger moon or the smaller? Should months follow one lunar cycle or attempt to honor both? Perhaps different regions would have adopted different calendrical systems. The tension between lunar and solar years, which real human cultures have struggled with throughout history, might have been compounded. Some civilizations might have developed lunisolar calendars based on the synchronization between one of the moons and the seasons, while others might have maintained separate calendars for each moon. Picture the calendrical complexity in the ancient Mediterranean, where Babylonian timekeeping, Greek geometry, and Egyptian solar knowledge might have developed in concert with a twice-mooned sky. The sheer necessity of coordinating time across trading networks might have pushed the development of mathematics and astronomy forward, or it might have made coordination more difficult, creating barriers to cultural exchange that our own history never faced. The naming of months themselves would have reflected this duality. January, February, March. These names in our calendar are rooted in Roman gods and carry echoes of Latin and older Indo-European roots. But in a world with two moons, perhaps every month would have carried the name of both. 12 months, yes, following the solar year as it does, but each month divided between two lunar cycles, or perhaps months would have followed one moon, and an additional intercalary system would have tracked the other. The language of time itself would have been different. How would you describe duration? 2 moons and a quarter phase, or 1 major moon cycle and 3 minor cycles? The very grammar of temporal description might have evolved differently, and the navigation charts, the star maps, the astronomical tables that filled the libraries of Alexandria and Baghdad and Chang'an, what would they have contained? The clay tablets of Babylon might have been thicker, covered in denser calculations. The precision required to predict eclipse conjunctions, to know when 2 moons would simultaneously darken the sun or pass before it, would have demanded even more sophisticated mathematics. Perhaps Islamic scholars during the golden age of mathematics might have been driven to develop algebra even earlier, pushed by the gravitational need to solve the equations of orbital mechanics. Or perhaps the added complexity would have seemed so overwhelming that certain mathematical developments would have been delayed, the human mind taking longer to untangle the mysteries of a doubled sky. If we were to look up at a sky that held 2 moons tonight, the first thing astronomers would have noticed, perhaps centuries ago, is that the night of total darkness would become almost impossibly rare. The choreography of eclipses, those moments when the moon slides directly between Earth and Sun, casting shadow across the land, would transform entirely. Where we now experience a total solar eclipse every 18 months or so, somewhere on our planet, with 2 moons dancing in the same sky, the frequency and character of those events would splinter into dozens of possible variations. Sometimes one moon might pass in front of the sun, while the other rode nearby, creating a dimming rather than a full darkness. Sometimes both might line up together, doubling the shadow, though the odds of such perfect alignment would be slimmer still. And sometimes, in a configuration we have no living memory of, one moon might eclipse the other as seen from Earth, creating what ancient observers might have called a celestial duel, one lunar body consuming its twin, only to release it moments later into the starlit sky. The practical challenge this would pose to modern eclipse prediction, to the careful mathematical models that now allow us to know, decades in advance, exactly where and when an eclipse will be visible, would be profound. Our eclipse predictions rest on knowing the motions of a single satellite with extraordinary precision, with 2, each with its own orbital period, its own inclination, its own slight wobble and gravitational influence on the other. The calculations would multiply in complexity, and yet, perhaps within reach. The mathematics would not be impossible, only demanding. Astronomers would become even more devoted to tracking, predicting, understanding. And we might ask ourselves, would the rarity of perfect darkness only deepen our hunger for it when it came? The tides themselves, as seen from the perspective of human science in this twin moon world, would be something of a puzzle to unravel. In our reality, tidal charts and predictions are taught in schools, used by fishermen and engineers, built into the infrastructure of coastal civilization. The tides follow the moon's dance with predictable grace. But with 2 moons, each pulling at the ocean with its own force, sometimes in harmony, sometimes at cross purposes, the system would resist simple elegance. When both moons aligned on the same side of Earth, their gravitational pulls would combine, and the tides would swell into what might be called king tides, even more profound than those we experience. But when the 2 moons opposed each other, one pulling high while the other pulled low, a kind of tidal standoff would occur, moderating the extremes. Tidal charts would become something more like weather prediction, still bounded by physics, still predictable in the long term, but with local variations and surprises that would require centuries of patient observation to fully map. For the practice of modern spaceflight, the presence of 2 moons would introduce what might politely be called complications. The Apollo missions, which required the careful calculation of lunar gravity and the timing of the spacecraft's entry and exit from the moon's sphere of influence, would have been exponentially harder to plan. Each of our 2 imagined moons would create its own gravitational well, its own orbit into which a spacecraft must be precisely inserted, and its own potential hazard. A spacecraft aimed at the larger moon might find itself caught between both gravitational influences, drawn off course by the smaller companion. The engineers would adapt, of course. Humans are resourceful. But the mathematics of launch windows, of trans-lunar injection, of the delicate ballet between Earth orbit and lunar descent, would demand deeper computation, more careful planning, perhaps longer mission durations, simply to account for the complexity. And yet there is something strangely beautiful in the thought of it. Imagine a crewed mission to one of these moons, looking back at Earth from the lunar surface and seeing not just our planet turning slowly in the darkness, but the light of the second moon rising over the ancient craters. The astronauts would be standing on a world that orbited a planet that was itself orbited by two companions. The perspective would be vertiginous, a reminder of how small we are, how precisely balanced our place in the cosmos truly is. The photographs they brought back would reshape our understanding of ourselves in the universe. They would become icons, not just of human achievement, but of the strangeness and variety of what worlds and skies could be. Satellites, the artificial ones we have launched in such numbers over the past several decades, would also have to contend with a busier sky. The geostationary orbit, that precious band of space some 22,000 miles above the equator where we park our communications satellites, would need to account for the gravitational perturbations of not one moon, but two. The calculations of orbital decay, of station-keeping fuel requirements, of the lifespan of a satellite in any given orbit, would all shift subtly. It is a small change in the context of the whole, but the kind of detail that engineers lose sleep over, that they must anticipate and plan for, that they must write into the code and the databases of mission control. And perhaps most subtly, the very enterprise of astronomy itself would be different. When we observe the cosmos from Earth, we must account for the moon's light, for the interference of lunar brightness in our observations of distant stars and galaxies. Telescopes are often scheduled to observe during the new moon, when the sky is darkest. With two moons, there would be fewer windows of true darkness. The night sky as a research frontier would become narrower, more contested. And yet, and here lies the strange irony, the presence of two moons might have driven earlier human civilizations to develop more sophisticated optical instruments, to push harder and faster into the science of light and motion, simply to understand what hung in their own sky. Perhaps we would have reached the telescope earlier. Perhaps our understanding of the cosmos would have deepened along a different path, not worse, but profoundly other. And yet this imagined world of two moons is not entirely a work of pure fiction, for somewhere in the outer reaches of our own solar system, a similar dance unfolds in the cold and silence, far beyond Neptune's orbit, where sunlight arrives as nothing more than a distant memory. A small dwarf planet and its companions circle one another in a gravitational waltz that defies the usual rules we think of as governing planetary companionship. This is Pluto and Charon, and their relationship offers us perhaps the closest mirror to what our two-moon scenario might actually feel like, were we standing on a world locked in such an embrace. For those who remember when Pluto held the title of ninth planet, before that distant world was reclassified into a new category of celestial object, there comes a curious surprise. Pluto does not simply orbit the Sun with a moon trailing behind it in the conventional sense. Instead, Pluto and Charon orbit around a shared center of gravity that exists in the empty space between them. This point, called the barycenter, lies closer to Pluto than to its smaller partner, yet it remains firmly outside of Pluto itself, creating a system that is almost binary in character. If you were to stand on Pluto's surface and look outward into that frozen darkness, Charon would not drift across your sky in the slow arc we are accustomed to seeing from Earth. Instead, it would hang nearly motionless in that portion of the heavens, suspended above a fixed region of the landscape, rising and setting with the planet's rotation rather than with its own orbital mechanics. This is a kind of tidal locking so complete and so mutual that it creates an asymmetry unlike anything in our more familiar corner of the solar system. What makes this even more extraordinary is that Charon, while far smaller than our own moon relative to Earth, is nonetheless of a size that seems almost companionable to Pluto. The proportion between the two is roughly 1/8 in terms of mass, whereas our moon is only about 1/80th of Earth's. This difference means that Charon exerts a gravitational influence on Pluto that is far more profound than our moon exerts upon us. The tidal effects of Charon would reshape Pluto's surface over eons, and the pull is so strong that it has locked both bodies in synchronized rotation, bound to one another so tightly that they have become, in essence, a binary system masquerading as a planet and moon. One might ask whether this is the most stable configuration imaginable for two orbiting bodies, or whether it represents a delicate arrangement forever on the verge of some subtle change. The answer, it seems, is something in between. The forces that brought Pluto and Charon into this configuration are thought to have emerged from catastrophe. Long ago, in the chaotic dawn of the outer solar system, Pluto likely suffered a tremendous collision with another object, one massive enough to send shockwaves through its structure and to alter its trajectory through space. Rather than shattering Pluto entirely, this impact instead set in motion a cascading series of gravitational adjustments that resulted in Charon being pulled from the debris, or perhaps from material that was already orbiting Pluto before the collision occurred. Over millions of years, orbital adjustments and tidal friction gradually synchronized their rotations until they became locked in that suspended dance that continues to this day. It is a reminder that the universe does not build its systems through gentle assembly, but rather through violence that is only gradually smoothed into something resembling peace. Yet Pluto and Charon are not alone in their demonstration of this principle. Much closer to home, nearer to the Sun and the warmth we associate with life, the planet Mars carries within its orbit not one but two small moons. And here again, we find ourselves contemplating a version of our thought experiment playing out in miniature. Phobos and Deimos orbit Mars at vastly different distances and with vastly different characteristics. Phobos, the larger and closer of the pair, orbits so near to Mars that it completes nearly 3 circuits around the planet in a single Martian day. From the surface of Mars, if you were to stand at certain latitudes, Phobos would rise not in the east as we might expect, but in the west, arcing overhead with a speed that would be almost dizzying, setting in the east after a journey of only a few hours. The second moon, Deimos, orbits far more distantly and moves at a slower pace, rising in the east and setting in the east as well, requiring nearly 3 Martian days to complete its circuit. The two moons would create a visual rhythm in the sky that is far more complex than what we experience with our single satellite, a constantly shifting pattern of light and shadow that would speak to 2 different cosmic periods unfolding simultaneously. What is particularly striking about Phobos and Deimos is that they are almost certainly captured asteroids, wanderers from elsewhere in the solar system who were drawn into Mars's gravity well and gradually trapped into stable orbits. This speaks to a possibility that even 2 moon systems need not be formed through collision or through birth from a single protoplanetary disk. Sometimes they arise simply through gravity and chance, when a passing object happens to arrive at precisely the right velocity and trajectory to be ensnared rather than deflected. In this sense, the 2 moons of Mars represent one path by which a world like our Earth might have acquired an additional companion. Had the asteroid belt been somewhat differently distributed, had some small rocky body wandered from its original orbit and encountered our young planet at just the right moment, Earth too might have accumulated not 1 but 2 lunar companions through such a mechanism of capture rather than collision. Phobos, moreover, tells us something else that is both beautiful and unsettling. This small moon, no more than roughly 22 kilometers in diameter, is slowly spiraling inward toward Mars. The tidal forces exerted by Mars upon Phobos are gradually siphoning away its orbital energy, and in perhaps 20 to 40 million years, this small companion will either break apart under the mounting tidal stress or will strike Mars's surface directly. This reminds us that celestial arrangements, while they may seem eternal when viewed against the scale of a human lifetime, are merely temporary configurations in systems that are constantly evolving. A second moon orbiting Earth would not remain in its initial orbit forever. Gravitational interactions, both with Earth and with our existing moon, would gradually alter its path over geological timescales, and somewhere in the distant future, if the system were destined to be unstable, we might witness a collision or an ejection. Or perhaps, given enough time and the right circumstances, we might find ourselves in an entirely new configuration, with our moons having somehow rearranged themselves into a harmony we cannot now predict. The systems of Pluto, Charon, and Mars, with its two small companions, offer us something invaluable, a grounding in real physics, a demonstration that these imaginative scenarios are not mere fantasy. Somewhere in the universe, wherever we look into the night sky, we find configurations that astound us and teach us what is possible. The dance of binary systems, the capture of wandering bodies, the slow reshaping of orbits through tidal forces, all of these phenomena are written into the fabric of the solar system around us, waiting to be observed and contemplated. And while we have walked in imagination through a world with two moons, we might pause to consider that the universe has already written this story in countless variations, across countless worlds that spin in the dark beyond our sight. And so we return, as all journeys through imagined worlds eventually must, to the single solitary moon that has actually graced our night sky for the past 4.5 billion years. The twin moons we've been contemplating throughout this long drift, their dance in the sky, their grip on our tides, their influence on the rhythms of life, they exist now only in the space of possibility, in the realm of thought where all the best what-ifs reside. Yet something unexpected often happens when we spend time imagining a world radically different from our own. The real world, when we return to it, becomes somehow more remarkable. Look up on a clear night, and you'll find that single pale disk hanging there in the darkness, patient and eternal, and there's something almost profound in its aloneness. For so much of human history, our ancestors looked at that same moon and felt none of the loneliness we might now imagine in it. Instead, they felt companionship, they felt watched over, they felt tethered to something constant, something that moved according to laws they couldn't yet understand, but could certainly depend upon. The moon rose. The moon set. The tides returned. The seasons wheeled past. There was a kind of perfect, almost musical simplicity in that singular presence. When we imagine two moons in the sky, we're imagining, in a way, a world more crowded, more complex, more contested perhaps. Two moons means two competing influences on the same world. It means the night sky divided by competing celestial bodies, each with its own gravitational voice, each pulling at the Earth in slightly different directions. But our actual moon, this one solitary guardian, it doesn't compete for dominion over the night. It rules alone and gently, and in that aloneness, there is a kind of grace. Think for a moment about all the light that reaches your eyes on a moonlit night. It is, quite literally, borrowed light. The moon itself produces no glow. What we call moonlight is simply the sun's rays, reflected off the moon's ancient, battered surface, and sent back to us across the void of space. It's a kind of cosmic relay, a gift of illumination that has traveled 150 million kilometers to the sun, then another 400,000 kilometers to the moon, and then finally, those last 384,000 kilometers back down to where you are, lying in the darkness. Imagine for a moment if that light were divided, if you were receiving illuminated reflections from two different sources, each with its own slight variations in hue and intensity. Would the night feel richer or somehow diminished? Would you gain something in the mathematical doubling of light, or would you lose something in the simplicity of it all? There's an interesting paradox in how the human mind responds to abundance. We often assume that more of a good thing must be better, more light, more choice, more options. And yet there's evidence, both poetic and scientific, that we find deep satisfaction in singular sources of meaning. The moon has been the moon for all of human culture. It's been singular, unique, unrepeatable. Our poets have written to it, our lovers have promised beneath it, our calendars have been built around it, our myths have accumulated in its craters and its silvery face. In a world of two moons, each would cast a shadow of the other, their myths would compete. their meanings would fragment. But here, in our actual world, the moon's meaning has had room to develop uninterrupted. It's been a symbol of constancy and change at once. It waxes and wanes, it appears and disappears, yet it always returns to the same portion of sky, moving through the zodiac with predictable grace. It's been a measure of time and a tracker of seasons. It's been a beacon for travelers, a calculator for farmers, an inspiration for dreamers. The fact that it's alone in the sky somehow makes all of that more concentrated, more intimate. You're not choosing which moon to look at. There's no decision to be made. There's only this one available presence, and in that availability, in that singular reliability, there is something deeply comforting. And what of the life on this world? If we had imagined correctly earlier, a second moon would have changed everything about the course of evolution, the migration of creatures, the rhythms that have shaped every living thing from the smallest tidal organism to the largest migrations of whales. But these are no longer imagined creatures. These are the actual animals that share this world with you, and their evolution, their behavior, their ancient biological clocks have all been calibrated to this one moon. The sea turtles that return to the beach where they were born, they navigate by lunar cues that have been reliable for tens of millions of years. The corals that spawn during specific lunar phases, releasing eggs and sperm into the water in a synchronized ballet of reproduction, they depend on this reliable rhythm. The nocturnal creatures that have built their entire lives around the pattern of moonlight and shadow that repeats with such perfect regularity, they know this moon. They've adapted to it in ways so deep and so fundamental that their bodies remember what their minds cannot even conceive of. In imagining a second moon, we've been exploring, perhaps without fully realizing it, what makes this actual world precious and improbable. Because that's what it is, improbable. Given the chaos of the early solar system, the collisions and near misses and gravitational dance of innumerable debris and proto-bodies, the fact that Earth ended up with exactly one moon, at exactly the right distance, with exactly the right mass to create stable, predictable tides and to slowly steal away the angular momentum of our rotation in a way that has actually lengthened our days and made complex life possible, this is not inevitable. It's almost miraculous in its specificity. The moon we actually have is not some default feature of planetary formation. It's a particular solution to a cosmic equation, a special arrangement that emerges from deep time and chance encounters and barely averted collisions. And we are the beneficiaries of that specificity. We are the creatures that evolved under the light of this particular moon, that learned to measure time by its cycles, that felt its pull in our blood and in our oceans, and in something perhaps even deeper, something less calculable but no less real. As this journey through impossible skies comes to its gentle close, you might find yourself noticing the moon differently the next time you see it. Not as a given, not as merely a permanent fixture of the night sky, but as something contingent, something that might have been otherwise but thankfully, improbably, remained exactly as it is. There's no competition in our night sky. There's no divided loyalty among the stars. There is only this one faithful companion, this lone bright eye that has watched over every human love affair, every human birth and death, every human reaching toward meaning and understanding. And in the profound quiet of the night, in the stillness that settles around us when we stop imagining and simply observe what is, the moon in its solitude becomes not a limitation but a kind of perfection, a single steady light in the darkness. A reminder that the world we have, with all its particular, improbable features, is not something to take for granted or to automatically wish different. It is, exactly as it stands, an extraordinary thing. A world carefully balanced, a night sky ordered and calm, and above it all, watching, reflecting, turning in its ancient orbit, our faithful moon, alone and enough, exactly as it's always been.